All right, here we're going to be talking about altitudes of right triangles. So every triangle has an altitude. It's really just how tall the triangle is when it's standing flat on one side. From one vertex straight down, perpendicular to the other side, that is an altitude. These exist in all triangles, but something really special happens in a right triangle. I'm just going to talk about what an altitude is in general. It is going from a vertex, and it's perpendicular to the opposite side. So it's dropping straight down to the opposite side. It's actually going to have three altitudes. Going from this vertex, we can also go straight across to make it perpendicular to this side. It's not going to be perfect. That's going to form a right angle. And then same thing with this vertex to its opposite side. So there are some relationships that actually happen with altitudes of triangles in general, but we're going to focus on altitudes of right triangles because that creates three similar triangles. We have this original triangle, ABCD. Nope, just ABC. That's our original triangle. When we drop that perpendicular from this vertex straight across, so from the right angle, straight across, and form two more right angles here, we're creating three similar right triangles. The original triangle, this small triangle, and this medium-sized triangle. This triangle, and our original triangle are similar to each other. And the reason for that is pretty simple. In our original triangle, we have a right angle, and we have, let's talk about this one first, we have angle B. So we have a right angle, and we have angle B. In this medium-sized triangle, we also have a right angle, and we have angle B. These two triangles have to be similar by angle. If I have a right angle and a common angle, I have a right angle and a common angle. By angle, those two triangles have to be the same. Same exact logic for the small triangle. Looking at the big one, again, we got a right angle, and we have angle A. Looking at the small triangle, we just created this right angle, and we have angle A. We have two angles that are in common between those two triangles also, so they have to be similar also. It's going to be really helpful. You want to do this every single time. You want to reorient these triangles so that they look the same, so that you can match up corresponding parts. So I'm going to redraw these two triangles, the two smaller triangles, so that they look like the bigger triangle. All right, first I'm going to do CDB. So right now, my right angle is on top, but in this triangle, it's on the bottom. I'm going to imagine this flipping over. I'm going to imagine this triangle reflecting over this line. So the right angle is going to come up top. That's angle D. C is going to come down to the bottom. And B kind of just stays put. This is going to reflect over this line. B stays exactly where it is. C just comes down a little bit. I'm going to do the same thing with this triangle. This one takes a little bit more. I'm going to imagine this rotating first. So I'm just going to rotate this. I'm imagining it tipping over like this. So now D is still here. A is going to come up. And C is going to drop down to the bottom. Now it's going to have the same orientation as this triangle, CBD. So I'm going to imagine what I just did. I'm going to imagine this now reflecting up and over. So C stays put. The right angle comes up to the top, which is really what I wanted, and A drops down to the bottom. That mental manipulation is not that easy to do. It's going to take some practice for you to get used to it. But really, it's important that we see all three of these triangles in the same orientation so you can match up corresponding parts. Triangles A, B, C, C, B, D, and A, C, D are all similar. Again, it's really by angle. Just because they share those angles. Angle A is shared really between all three triangles. Angle A exists here in the big triangle and in the small triangle. when you reorient it, angle A jumps to here. Angle B exists in the big triangle, and in this medium-sized one, when you turn it around, it ends up right there. Alright, so let's see how this is used to find some missing side lengths. So we're trying to find DB, and we know AD is 4, and we know CD is 6. Going between these two triangles is the easiest version of this. I'm just going to imagine this triangle tipping over and ending up looking like that. So I'm going to redraw that triangle, and you should do the exact same thing. You should redraw that triangle every single time. If this tips over, C comes down to the bottom, A comes up, D stays put, but it rotates. So I have AD of 4, CD is 6. Now I'm using this triangle, and this new triangle that I just drew. Really, it's this triangle just tipped over that triangle to set up my proportion. This side length, one leg compared to the other leg, 6 over x. That equals this ratio also, 4 over 6. I'm going to cross multiply. Yep, 36 equals 4x. And so x is 9. Same kind of thing on this one. I have AD is 2, DB is 8, CD is what I'm trying to find. So I'm going to imagine this reorienting the exact same way. Just tip it over so that C ends up where B is. C drops down, A comes up, and D just pivots. AD is 2, CD is x. Now I have enough to set up my proportion. I can compare 2 to x and x over 8. Those have to be the same. So I'm going to cross multiply and get x squared equals 16. When we do the square root of this, technically this could be a positive or a negative version of that. X could be positive or negative 4. Problem is, when we're talking about a side length here, we can't deal with that as a negative. You can't have a negative distance. So x just has to be positive 4. Alright. Sometimes reorienting this is not that easy. It's not as simple as just tipping this over. You have to really reconstruct the entire triangle. So I'm going to do a few more examples here. AD is 3, DB is 6. We're looking for AC. Alright, I'm going to redraw all of these triangles so that they look the same. ABC I'm leaving as it is. I'm going to redraw the medium-sized triangle and the small triangle to look like ABC. So this triangle, I have to imagine D reflecting over, and then I rotate a little bit, but really the big mental manipulation here is D flipping over there. So my right angle comes up, that's D. C comes down to the bottom, and B kind of just pivots right where it is. So DB is 6. I don't know DC, and I don't know BC either. All right, to get this one to that same orientation, I have to first imagine this tipping over. So this triangle, I'm going to just sketch it there. 3 comes up, X is the hypotenuse there. I don't know CD. C drops to here, D pivoted, and A came up to the top. So now it looks like this one. Now I need to do what I just did. I'm going to imagine this reflecting up. So D jumps up to the top, A comes down to the bottom, C stays where it is, it just pivots. So AD is 3, AC is X. That is everything I know. Now I just need to think about what I can actually use here. So this triangle only having one side pretty much is telling me that this triangle is not going to be used here. I have two side lines here, and I have those same two side lines here. So X over 9, x over this entire length here of 9 is equal to 3 over x. Those are corresponding sides there. So x squared equals 27. We are not going to write decimals as answers here. We're going to write simplified radicals. So we want to think about what perfect square goes into 27. That's 9 and 3. So we're going to take the square root of both of those. Really, we're imagining taking the square root of both sides. The square root of 27 splits into the square root of 9 times the square root of 3. The square root of 9 is 3. The square root of 3 doesn't simplify. Just going to say it's radical 3. This is the process that you want to do each time. You want to reorient these triangles to figure out what corresponding sides you have. All right, on the next one, we got BC and AD, and we're looking for DB. All right, so same thing. I'm going to reorient this triangle. D comes up to the top, C drops to the bottom, B stays put. So DB is X, CB is 6. I'm not going to do the third triangle because I notice that I have everything that I need. X over 6 is going to equal 6 over this length is these two put together, or just 5 plus x. So x over 6 equals 6 over x plus 5. All right, I'm going to cross multiply. X gets distributed into both terms here. That becomes x squared plus 5x. 6 times 6 is 36. If you're comfortable using Desmos, use Desmos. I personally like factoring, so I'm going to end up factoring this. This is quadratic. I'm going to bring 36 to the other side. You get x squared plus 5x minus 36 equals 0. And I'm going to factor that. I'm thinking about what's going to multiply to give me negative 36 and add up to give me 5. It's got to be a positive 9. To give me a positive 5, it's got to be a positive 9 and a negative 4. Those two multiply to give you negative 36, and they add up to give you 5. So this is the factored version of that. X plus 9 and x minus 4. We want to think about what x value would make this equal to 0. So it's really going to be the opposite signs here. It's going to be x equals negative 9 and positive 4. Remember, we can't really use a negative value for x here. It can't have a negative length there. So it's got to be the positive version. It's just x equals 4. Or just 4, really, the length. Nobody said it was x. I'm just making that up. Just 4. All right, DC is 4. DB is 6. We're looking for AD. This is the easiest version. When we have these three lengths, I can just compare the small triangle to the medium triangle, imagining this tip over. So A comes up to the top, C goes down to where B is, D stays put, just pivots. So AD is X, CD is 4. That's enough for me to compare these. 4 over 6 is X over 4. So we're going to cross multiply. You get 16 equals 6x. This one we could just write as a fraction. That's 16 divided by 6, or 8 over 3. If you want to write that as 2.6 repeating, you also could do that. You can write that as a decimal or as a fraction. All right, last one together. AB is 12. DB is 8. What's the length of AC? All right, so first I'm going to simplify this part. I'm just going to change that into 4 on this side and 8 on that side. And now I'm going to redraw my triangles. I'm going to take the medium-sized one and reorient it. So D comes up to the top, C drops to the bottom, B stays put, just pivots. So 8 comes up to the top. That is not really going to be helpful. If I look at how that compares to this side, or these sides that I have, it's not really going to help. It doesn't correspond with anything that I'm given already. So I'm going to need to use this small triangle. So first I'm going to imagine that tipping over. C comes down, D stays put, A comes up. So it's 4x, and I don't know that one. Now I'm going to do that second flip. I'm going to flip this over. So D comes up to the top, A comes down to the bottom, and C stays put and just pivots. All right, that is what I wanted. I have corresponding sides that are labeled either with variable or a number. So x over, I'm going to use that entire length of 12, is equal to 4 over x. So x squared equals 48. Again, I want to think about a perfect square that goes into 48. That would be 16. So the square root of 48 is the same thing as the square root of 16 times the square root of 3. Square root of 16 is 4. Square root of 3 does not simplify. That is all we can do with that one. If you're not sure about simplifying radicals, you can always change this into decimal and then make sure that this is the same decimal. Or if you're given multiple choice options, you don't even have to simplify on your own. You just change that into a decimal and compare to the answers. All right, this is going to take some practice, but once you get used to it, it's not that tricky. It's just about orienting triangles in the same direction. If you need help, now's the time to ask.